SwayamPrabha. Digital India. Educated India.
So now we will see in the second part of the lecture today the fundamentals for implementation of closed loop control. This will need for this practical kind of part in the assignment, and we'll talk about more. It's very important topic for practical implementation with your microcontroller. So please go through this lecture meticulously to understand like a lot of these fundamental conceptual details. This is more on a philosophical level, and so that you will be able to kind of use these ideas and things that are talked about for actual making sure your motor runs in the closed loop the way we desire it to happen. Okay, so let's get into more details here. So this fundamental principle here for any automatic control system, which we are talking with respect to the example of motor for our case, there are these following three tasks that happen continuously. One is reading of the sensors. So it's not potentiometer, it's encoder in our case. Okay, so this please update that this is encoder in our case, not a potentiometer. So we read a sensor which is encoder in our case, then compute control law, which is maybe PD kind of a control, and that we have seen in the feedback concept of feedback, and or maybe you might have seen some of these control algorithms in your automatic control kind of courses previously. And then we need to give this control input to the actuator. So how do you give this? We give this via PWM interface. Okay, specifically we keep on changing the duty cycle depending upon what is the computer control input in every step of the sampling. Okay, so this is running continuously every periodic kind of a time. So that is called like sampling time. And how do you set up the sampling time, which will see that okay, that sampling time is set up by using interrupt timer module. Okay, so typically all microcontrollers will have this interrupt timer, programmable interrupt timer module, which will allow you to set up this interrupt service routine. So which will run run every sampling time that you have set in that routine. Now let me explain you this concept. What is this interrupt and timer together would work. So concept of interrupts, I'm presuming you know. Just to recap, I'll give you the that okay, you are reading a book and your mom calls, okay, and your phone is ringing. What you hear the phone, and I hope you want to take up that call, okay. And what you do is like you put a bookmark in the book and go pick up the phone. Of course, I'm assuming that you want to take up the call, and then you reply to the call, you finish the call up, and then again come back to the same bookmark and like open the book and start reading it. Exactly the same kind of a concept is there for the interrupts. Okay, so microcontroller is kind of doing some task, and on some pin some signal comes, like some pulse comes, and that pulse, this is like an interrupt pin specifically designed for that purpose. So on the interrupt pin, when this pulse comes, microcontroller will halt the current task for a moment, and it will serve some other task which is defined for that particular pin. Okay, so that task will be called as interrupt service routine. Okay, So that task will be executed, and then again microcontroller will go back to its original point or your main program and start executing from where it has halted previously. Okay, now these pulses that are coming on this pin, if every time this pulse comes, like now the microcontroller has to execute some task which is called interrupt service routine. And whatever these three operations I have mentioned here, okay, these all three operations, they will be typically written in the interrupt service routine. Okay, so they will be executed every sampling time. Now for them to get executed every sampling time, this pulse needs to come on the pin at every sampling instances. Okay, so typically these pulses are generated on some kind of a timer module will do that. Okay, so counter timer module will have a job to develop this kind of a pulse every whatever sampling time instance, and this pulse is internally connected. You don't need to do any connections, nothing in your microcontroller. Like these modern microcontrollers, you don't need to do nothing. It's software, only the software that you need to kind of write, because these pins are already internally connected, so that this pulse will get generated in the timer module and it will go on the interrupt pin, and these pulses now are programmed to come regularly in some kind of a, the way you have a square waveform which is periodic. These pulses are coming now in a periodic kind of a way, and when these pulses are coming, every pulse comes, you do these three tasks. Okay, or every pulse comes, you execute your interrupt service routine will get executed, and you keep on doing this task. And how do you kind of program for this part of setting up sampling time or programmable interrupt timer module to program to give you some kind of a facility to have something written in the interrupt service routine and getting executed every sampling time. Okay, so you can do that first, so that you can set up your sampling time properly, and then now you can slowly start putting things in the interrupt service routine of this module. So for example, if you have written PWM program, you need to kind of see, okay, what are the parts of that PWM program which can go in the main program, and what are the parts which should come in the interrupt service routine. You can bifurcate. For example, you just want PWM duty to be changed here. Okay, so all other commands in the PWM routine should not, like, or the other registers should not change. So our other functionalities should not change. So only the functionality which is giving you the handle over PWM duty cycle, that can come in the interrupt service routine. Okay, like that, you think what will be coming from the encoder interface into your first reading sensor kind of a part. Okay, like that you need to start thinking and programming. Okay, and you don't need to do any for loop. This is very important. Don't set up any for loop for doing this. Once you are putting these things in the interrupt service routine, you are rest assured that they will run every sampling instance. Okay, they'll run continuously over and over again. You don't need to put any for loop whatsoever for this purpose. Okay, we'll discuss a little more detail. Okay, why we keep this as a interrupt based sampling time programming, as we discuss, like, the sampling and other issues in more detail. Okay, so we want every fixed known sampling time for the operation to happen every periodically, and this job will be done. Okay, now so to put all these things together, here we are using the encoder position, feedback coming from the encoder. Okay, so this is the first part here. Okay, reading sensors in encoder in this case, and then like we'll use some kind of a proportional derivative control law. So this expression typically will be of this kind of a form. So you'll have some kind of a desired position and you have actual position, and these things will be this desired position. As you see later, like we'll see what kind of a form we should have for the desired position, so that we keep on observing, like, once you have implemented, we keep on observing how our control is performing. Those kind of things we'll see. Then how do we apply this to control law to the motor? So see, this control expression may give some negative value, okay, depending upon what are the values of these. So how we, when if the value is coming negative, how do you see PWM duty is only positive value 0 to 100? Then we need to kind of do something to control motor. Okay, so we need to kind of give something to kind of reverse the direction of the motor. If the direction here the computation is negative, that is what we need to do. So you know how to do the direction reversal. So those are the things that we need to implement. Okay, so that's what we are discussing. What if this value is negative? We need to use the in A in B pins of the driver to get reversed to change the direction of the motion. Then again, this question is what should be set as a desired position for this job to happen properly. So because if we just put some kind of a constant value in desired position, you think what will happen, and then we want to observe this happening properly, then we need to kind of set these values in the appropriate way. Okay, so these are all the questions that you ponder over and think yourself and see what solutions come to your mind for this, and then you proceed to the next part. Okay, so this pondering over for you is important here. So now we'll see, this is a control feedback. So now if what will happen if we keep the desired position constant? Okay, then you imagine like their program is start running in the interrupt service routine. You'll read the direction, you read the actual position, and your desired position is constant, and then like the actual position will start getting control to the desired position value in some way. And then once it reaches desired position, it will stop, it will do nothing. Okay, or it reaches close to the desired position, it will stop there only. Okay, you start moving it, you'll find some resistance to move from that position if you externally start moving the motor, but otherwise it will do nothing after that. So this is not a great way of like continuously observing how your control is performing. You want to kind of have some kind of a handle over seeing that okay, this control what I'm implementing is continuously doing something. Okay, so for that purpose we set up the desired position to have like okay, if it reaches the final position, then like after some time, after steady state is reached, you change it back to 0. Okay, so you make it 0 again, and again you kind of let it come to 0, and again you take it to the desired. So you can do that continuously. Okay, so otherwise like if you want to observe the control law working multiple times, same kind of a control law working multiple times, you will not be able to do that. So you can do that by using the desired position. So now how do you generate this kind of a desired position? Think about some algorithm to generate this. So given that you have this now to be written in the interrupt service mode routine, which is kind of a loop which will run continuously every sampling time. Okay, so think about that. Suppose if we want like the square waveform to have some certain kind of a time duration, that okay, this desired value will be held constant for this time duration, and then it is brought to 0 for same time duration next. Okay, and keep on doing that. Okay, so what kind of algorithm comes to your mind? You need to kind of think about, and you need to get used to now writing things in the interrupt service routine which is executing every sampling instance. Okay, so if the sampling time is t and this time for your square waveform is say t1, then you need to kind of see okay, how many number of sampling instances have to pass by before I change this value, and like that we need to kind of these are some of the hints I'm giving for you to write this or develop this algorithm for the program. Okay, so this kind of a square waveform you can generate for the desired position. So this desired position. So this is not a tracking. Okay, don't confuse that this is becoming tracking. No, this because we are suddenly changing this position. We are not kind of like taking this smooth kind of a trajectory here. It's a multiple times you are observing the regulation here. Now, another question. Okay, what should be amplitude of the square wave? Okay, so this that you can compute based on the encoder counts that you are you are getting output from the encoder. Okay, so say if you are getting whatever roughly 1,000 counts for one revolution, then you can plan. Okay, I want to move one revolution or two revolution or 90 degree, 80 degree, like that. Based on that, you can plan this number of counts. Okay, and you can attach some kind of a small cardboard or plastic wheel to the motor. Maybe you can make it out of the the visiting cards. They are kind of stiff stuff there to attach, and then you can put a pointer there to kind of know the position. So like that you can do. Then what should be frequency? Frequency should be large enough so that you observe the controls. So your control is happening like that. It is controlling, and then it is becoming steady state. There should be some duration left beyond that, and then it should be change. So this typically frequency of the square wave should be very very low, so that you are able to observe your control nicely. So we can observe the system response visually. Okay, what will be typical response of the motor? If you can sketch on this desired response, what is the actual response going to be? You can get something of this sort. Okay, so you can look for you'll get some response of this kind when you give this square waveform. Okay, and then we want to kind of get this data out of the microcontroller, and maybe we should be able to put it in the MATLAB to observe this response. Okay, this response we can observe by graphing functionality to see in the real time in the coming on the graph. Okay. So of course we need to initialize some value to be 0 and then proceed. So it may so happen that you will find that your response observed is exactly same as the desired position. Okay, you may not observe any undulations here, especially if you are observing for just the speed of the motor. Okay, in the open loop, even some kind of a instead of x desired, it's like a PWM which is given some duty cycle. Okay, not really PWM, but speed. Sorry, this is like a speed that is desired. PWM desired will give you position continuously going in one direction till the time this PWM is getting to 0. Okay, but what I mean is here, if you have a constant voltage given to the motor, and we are observing this x dot desired, then that response is going to be like that. Okay, it will go like a first order kind of a function. But if your inertia is too low, then the sampling time that you have chosen might be too large for capturing the initial kind of a that typical for first order kind of a response capturing may not happen. So you may find that okay, oh my the waveform for the speed now is coming as a straight. So then you need to decrease the sampling time to make sure that okay, you are able to observe that transient that is going there. These are kind of small tricks that you'll need to learn as you build your practical understanding of the system. Okay, so this typical program, you can use this following what you say hints to develop on your own. So you need to initiate, configure, and enable interfaces, all the interfaces that you are needing for this closed loop system operation to be working. PWM, interrupt, then encoder QI module, and any other variables you want to define. You can define them to begin with. Okay, this all can happen either in the main program or in the like say some of the definitions can happen before main program. Okay, when you use the commands like include something and things like that. Okay, then in interrupt service routine, this is very important. Okay, we'll need to do these three operations that I was talking about. So in this you need to make sure like no initiation or configuration kind of functionalities, okay, from TIVA should come into this interrupt service routine. Configuration or enabling kind of interfaces, they should not come in the interrupt service routine. It should have just like for example, from QEI interface, it should just reading the value of encoder, whatever function is there, or reading the speed of encoder, whatever function is there, that can come up here, because that is a thing that will be continuously changing. All other things are going to be for constant for this particular program. Okay, so only these changing parts should come, which are changing every interrupt cycle, that should come. Now then you have to compute control by using the feedback law. We have seen some law, proportional law or something like that, and implement. Now implementation aspects will involve a couple of things here, okay, that we need to be sensitive to. Say for first, make sure that the variable definitions are appropriate. Okay, you have used signed and unsigned integers or floats or whatever, these definitions are made in a way that it is conducive. Say for example, if you define for the control input the unsigned integer, then your negative part of the program control will not work at all. Okay, so those kind of things you should be careful about. Then control input should not exceed some maximum value in any case. Okay, so put the value with some kind of a limiting saturation function. And then third part is if control computed is negative, then how do you kind of handle that? What does it mean? It means that okay, I need to reverse the direction of the motor with some same so you will make it positive before applying to PWM duty. So PWM duty is like a mod part of the control input command, and the sign part positive or negative will be used to change the direction pins. Okay, this is a very important kind of a baseline for control implementation to happen. Okay, these 2 points are coming, so you can maybe kind of put some kind of a small function to make sure that okay, this will happen before control is implemented. Okay, then you need to update any variables. Okay, so previous position needs to be updated for derivative computation and things like that, or desired trajectory need to be updated now. Okay, so that functions will come here, or they can come at the start also, no harm. Okay, somewhere they should come in the interrupt service routine. Okay, so how do you compute derivative control action? Okay, do you know this difference formula? You can use that and do that. Okay, so it's very straightforward kind of a thing. Only thing the question is, how do you get this previous how do you know what is previous x position? Okay, position x, I know current position, but how do I know previous position? So since we don't in the interrupt service routine when we are working with, then we need to store the previous values. Okay, so we store the current values which will be available as say x previous for the next sampling instant to come. Okay, so that's how we store the previous value every in that's what every sampling instance. Okay, so we update these values to kind of make sure that our previous values are available. As I said here, update any variables. Okay, so the variables need to be getting updated. So x previous will need to get updated to current x current to make sure that okay, it is now the current value will become previous value for the next sampling instance. That is a kind of a thinking philosophy that one should use. So if you want 1 or 2 or 3 previous values, you can do that by the same way. Okay, and so this is some additional task you can think about. Say if you want to generate sinusoidal waveform as a desired waveform instead of the square waveform that I have we have seen here, how do you kind of do it and implement in the interrupt service routine? Okay, so this is algorithm one can think about. Okay, so this is just an extra task that you can think about and do. Okay, So I think this is good enough kind of a primer for you to kind of get started and implement practically any kind of a control on your microcontroller. And then we'll have interesting kind of things to talk about with the practical results that you get out of such implementation. So we'll be able to talk about in your assignments slowly as we progress. Okay, so maybe we'll stop here for now, and then we'll have some more part with the lecture coming up. Okay.